Let's take a look at the basics of parallel resistors. To begin, let's look at a single resistor. It has a resistance R, and we can define the current passing through the resistor and the voltage that appears across the resistor. Ohm's law describes the behavior of the resistor. It says that the voltage is equal to the current times the resistance. We see that the voltage is proportional to current, and the resistance is the proportionality factor. Let's now consider the case of two parallel resistors. Here's the first, and here's the second. Now, the distinguishing feature of parallel resistors is that the current I entering this end splits into two parallel paths. I'll call those different currents I1 and I2. Eventually they rejoin to make the original current I. The idea is that the current follows multiple parallel paths, and that tells us that it increases the conductance of the path followed by the current. I'll keep track of those resistors as R1 and R2. Also notice that the voltage that appeared across that single resistor, V, also appears across R1 and R2. So another distinguishing characteristic of parallel resistors is that each resistor has the same voltage. Now, conductance, which is denoted by the symbol G, is equal to the reciprocal of resistance. Or we could say that G is the inverse of resistance R. Now I've rewritten Ohm's law here a bit. You can write I equals V times 1 over R, but we recognize that 1 over R is the same thing as conductance G. So another way of writing Ohm's law is current is proportional to the voltage, where the conductance is a proportionality factor. Now, by Kirchhoff's current law, we see that the current I is equal to the sum of the currents I1 and I2. Now, based on the rewritten version of Ohm's law, we can write that I is equal to V times G1 plus V times G2. We see V is common, so I'll pull that out. Now, matching terms, we see I, V, and then this sum, G1 plus G2, apparently is the equivalent conductance of the parallel resistors. Rewriting G as 1 over R, we find that the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistors that are in parallel. Solving for equivalent resistance, we have this expression for two parallel resistors. Let's generalize this to an arbitrary number of resistors. Imagine that we have n resistors in parallel, giving us n distinct paths for the current, and all of those current paths are happening in parallel with each other. And again, each time you add another resistor in parallel, you increase the conductance of the overall resistor network. Another way of saying that is that we decrease the equivalent resistance. So we can calculate the equivalent resistance of n resistors in parallel by forming their individual reciprocals, adding them up, and then taking the reciprocal of the result.